The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting, do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. You'd think after all the times I've read this that I would do a better job. Oh, well, okay. So we're going to look at a problem from section 11.5. This is number 35 that came in by request. It says Kuwait, located at the head of the Persian Gulf, has one of the greatest population growth rates in the world. Bulgaria in southeastern Europe has one of the smallest. Use an exponential growth decay model to complete the table. So we're going to use the formula A equals PE to the RT power. All right. Now, for the first problem, the population is 2,789,132. So P would be 2,789,132. And the growth rate would be 3.501%, which is 0.03501. Okay, moving the decimal point 2 places to the left and dropping the percent sign. So let's see, let's do this. For our second problem, the population is 7,148,785. And the growth rate is negative 0.768%, which would be negative 0.00768. Is that right? Let's see. 1, 2. Yep. Okay. So we have our information. So for the first one, Kuwait, A is going to equal 2,789,132 E. I forgot one thing. It said estimated population in 2021. So what would T equal? That would be 11 for both cases. Sorry about that. Okay, so E raised to the 0.03501 times 11 power. So 2,789,132 times e to the 0.03501 power, and then times 11, and I get 4099399.241. So that would be 4,099,399. Okay. For the second scenario, which is Bulgaria, where in fact it's not growing, it's decaying, so that the population is shrinking, A would be 7,148,785 e to the negative 0.00768 times 11 power. I was looking at the wrong number there. Okay, 7,148,785 e to the negative 0.00768 times 11, and A is 6,569,662.177. So to the nearest whole number, you would have 6,569,662. All righty. Do any of you present right now have any questions before we go on? Okay. So now let's go back to a scenario that I introduced the other day, I believe, and I said something like 2 cubed is 8, 2 to the 4th power is 16, 2 to the x is, and I don't remember what number I chose, but let's just pick, let's pick 11, okay? And then I said 2 to the x power equals 11, using logarithms, which we've been doing here for a few lessons. We could write the equivalent statement, which would be log base 2 of 11 equals x, or x equals log base 2 of 11. But the problem is, most of our calculators, most of our scientific calculators, don't have a log base 2 button. Some of you might have a calculator that has this button, where it has a little box for the base and a box for the quantity you take the log of. If you do, then you can punch that straight in. But if you don't, then you need to use the change of base formula. And the change of base formula, this is the one thing we're going to look at in section 11.6, says this. If we have log base b of x, that's equal to log base a of x divided by log base a of b. So we go to a completely new base, but the same base for both, the top and the bottom. And again, keep in mind the base has to be positive, but not equal to 1. And we take this quantity up above, and the base here becomes the quantity down below. So for instance, we could write log base 2 of 11 as log base 10 of 11 over log base 10 of 2. Or we could write it as the natural log of 11 over the natural log of 2. But we want to use log base 10 or log base e because those are the ones that all our calculators, all our scientific calculators have. They should have those 2 buttons on it. Okay. You don't want to do log base 10 on top and log base e on the bottom. Okay. You got to have the same base on top as on the bottom. All right. So let's punch each of those into the calculator. We should get the same answer for both. So log base 10 of 11 divided by log base 10 of 2. And I'm coming up with 3.45943, et cetera, that if I take the natural log of 11 divided by the natural log of 2, I get the same thing as I got up there. Okay? Now, log base 10 of 11 does not equal the natural log of 11, but the ratio of this to that is the same as the ratio of this to that. But you got to use the same base, either both base 10 or both base e. All right. So now I'm going to look at some examples from 11.6. And here we go. We have log base 3 of 7. It says, use the change of base formula to find each logarithm to 4 decimal places. So that would be log of 7 over log of 3. I also could have used natural log of 7 over natural log of 3. Let's see. Log of 7, close it up, divided by log of 3, close it up, and I get 1.77124 to 4 places. That would be 1.7772. I wrote that incorrectly because I can't read my own writing. So let's go back here and fix that. Originally it was 1.77124. So this would round down. There we go. Sorry about that. My 1 turned into a 7. Shouldn't have. Okay, here's another one. Log base 5 of 10. I'm going to use natural log this time. So that would be the natural log of 10 over the natural log of 5. So natural log of 10, close it up, divided by natural log of 5, close it up. 1.43067 to 4 places. The 7 would round up, giving me that answer. When I say close it up, what I mean is So in my calculator, natural log 10, close it up, divided by natural log 5, close it up. Because if you don't put that second parenthesis there, it thinks all of this goes in there, and you don't want that. Okay. Do you need any more examples of this? I'll take that as a no. So we're going to go on to section 11.7. All right. And let's see. It says solve each equation. Let's say we've got 3 to the x plus 1 power equals 27. Because exponential and logarithmic equations are one-to-one functions, if we can write this equation so that it has the same base on both sides of the equations, we can assume the exponents are equal. So what I'm going to do is I'm going to write 27 as 3 cubed. Why? Because now I have the same base on both sides of the equation, which means the exponents are now equal. Solving this equation, subtract 1, x equals 2. Let's check our work. If x is 2, 3 to the 2 plus 1 equals 27. 3 cubed equals 27. 27 equals 27. So it checks. Any questions about that particular problem? All right, let's take a look at another example. Let's say we've got 8 to the negative 2x plus 1 equals 1 over 64. Well, the base on the left is 8. I could rewrite 1 over 64 as 1 over 8 squared, which I could write as 8 to the negative 2 power. So here we're doing something a little unusual. Typically, we take a base, and if it's raised to a negative exponent, we move it on the other side of the fraction bar to make it a positive exponent. But here, we're trying to get the bases to match. In order to do that, I need to turn this into a situation with a negative exponent. But now that they're both base 8, negative 2x plus 1 equals negative 2. The exponents are equal. Solving for x, we'll subtract 1 from both sides of the equation. We'll divide by negative 2, and x equals 3 halves. Let's check our work. If x is 3 halves, 8 to the negative 2 times 3 halves plus 1 equals 1 over 64. 8 to the, well, the negative 2 times 3 halves would be negative 3 plus 1, which would be 8 to the negative 2, which would be 1 over 8 squared, which would be 1/64 equals 1/64. So it checks. Any questions about that? Okay. Now, let's say we've got this situation. 7 to the x power equals 12. Well, now we've got a problem because I don't know about you, but I can't think of how to take 12 and write it as 7 to some power, or 7 and write it as 12 to some power. So getting the situation where we have the same base on each side doesn't seem feasible. So let's go to plan B, or maybe we should call it plan L for logarithms. We're going to take this exponential equation and change it into a logarithmic equation. So that becomes log base 7 of 12 equals x. Okay with how I did that? I'm going to rewrite that as x equals log base 7 of 12, only because now I'm going to continue and use the change of base formula and write this as log of 12 over log of 7. I will then punch that into the calculator. And let's see, log of 12, close it up, divided by log of 7, close it up. I get 1.276989, et cetera, and it says approximate to 4 decimal places. That would be right here. The 8 would round up, so I'm going to get 1.2770. Okay. Now it says give an exact solution and then the approximate solution. So this would be the exact solution. This would be the approximate, or this would be the approximate solution. Okay. You could also argue that this is the exact solution, though it's just not in a form we can punch into the calculator. All right. Let's see here. Let's see, I've got 5 to the x plus 1 power equals 3. Again, I can't take that and change 3 to some power of 5, but I can write log base 5 of 3 equals x plus 1. Solving for x, I could subtract 1 from both sides. So log base 5 of 3 minus 1 equals x, or x equals log base 5 of 3 minus 1. Now, it's not the log of the quantity 3 minus 1. It's the log base 5 of 3 minus 1. So this is the thing you're taking the log of, not that whole thing, okay? Now, come on, eraser. Using the change of base formula, this becomes log of 3 divided by log of 5, and then minus 1. Okay, so the minus 1 is not part of the logs. So I've got log of 3, close it up, divided by log of 5, close it up, minus 1, and I get negative 0.31739. The 9 rounds up, so negative 0.3174. Okay. Any questions about that problem? Let's take a look at another example. Let's say I've got e raised to the 3.3 t power equals 9.1. Well, I have no idea how to take 9.1 and write it as e to some power, but I could change this to a logarithmic equation, and I'd have log base e of 9.1 equals 3.3t. But isn't log base e natural log? So I get the natural log of 9.1 equals 3.3t. Dividing both sides by 3.3, I get, oops, I shouldn't have crossed out the t there. I get t equals the natural log of 9.1 over 3.3. I don't need to use the change of base here because I've got natural log in my calculator. So natural log of 9.1, close it up, divided by 3.3, and I get 0.669174067, rounding to 4 places. The 7 rounds up, 0.6692 is our answer there. Any questions about that? Okay. Now, let's say we've got this situation. Log of 5x equals 4. Well, this is a logarithmic equation. I could change it to an exponential equation, but what's the implied base? Anybody?
10.
Good job, 10. So now this becomes 10 to the 4th power equals 5x. Divide both sides by 5. X equals, let's see, 10 to the 4th power would be 10,000. Divided by 5, x would be 2,000. Questions there? Let's say we've got the log of the quantity 2 minus x equals 3. So again, there's an implied 10 there. So 10 cubed equals 2 minus x. 1,000, 10 cubed, equals 2 minus x. Subtract 2, 998 equals negative x. Divide by negative 1, x equals negative 998. Any questions there? All right, let's say we've got a situation where we've got the log base 10 of 3 minus 2x equals the log base 10 of x plus 24. Again, since logarithmic functions are one-to-one, if we're taking the log with the same base of both sides of the equation, we can take the quantities that we're applying the log to and set those equal. So now, let's see, I'll subtract x. 3 minus 3x equals 24. Subtract 3, negative 3x equals, equals 21. Divide by negative 3x equals negative 7. Let's clean up that mess a bit. So this would be negative 3x equals 21. Divide by negative 3x equals negative 7. Okay. Now, let's take a look at some application problems. But before we do, we need to talk about the idea of half-life. Let's say that I put 128 Snickers bars in a refrigerator, and I come back 1 week later, and there's only 64 bars in the refrigerator. So half of them have disappeared, okay? And then I come back 1 week later, and there's 32 Snickers bars. So half of the ones from the 64 have disappeared. And then 1 week later, we have 16, and then we have 8, and then 4, and then 2, and then 1, and then a half, and then a fourth, etc., etc. So every time a period of a week goes by, half of those Snickers bars that were there at the beginning of the week disappear. So we would say that the Snickers bars have a half-life of 1 week. Every week, half of them die off or disappear. Okay? Now, two half-lives does not a whole life make. In other words, if you lose half of them in 1 week, that doesn't mean you lose all of them in 2 weeks, because each time you lose half of what was there at the end of the previous week. Now, if we had something like y equals 1/2 to the x power, that would be a decreasing function, and each time x increased by 1, y would be cut in half. Okay, we looked at this, we graphed this the other day, I believe. But what if I had this instead? Instead of having y equals 1/2 to the x, I had y equals 2 to the negative x. If I wrote 2 to the negative x with a positive exponent, wouldn't it be 1/2 to the positive x? But I could also say that, well, 1 to the 1 power or 2 power or 3 power or whatever power is still 1. So I could write it like that. And in fact, I could write it like this. My point is, what I'm trying to get you to see is that that is the same thing as that. Why do I want you to see that? Because the formula that the authors use for half-life looks like this. Instead of using a base of 1/2, they use a base of 2, but they have a negative exponent. So for instance, we could have done this. Okay, but that's not what they did, so I'm going to stick with what they've done. But keep in mind, because that is a negative exponent, it causes the thing to decay. All right, now, so let's go back to this. In this formula, A naught, or A sub 0, the A with that little circle, is the beginning amount. A on the left side of the equation is the ending amount. T is the amount of time that passes, and H is the half-life, the amount of time it takes to lose half of the substance. Okay? Here is a problem. It says, let's see, tritium decay. The half-life of tritium is 12.4 years. So the half-life is 12.4 years. Okay? How long will it take? So time is the unknown. For 25% of a sample of tritium to decompose. It doesn't tell us how much we have in the beginning exactly. It doesn't tell us exactly how much we have in the end. But it tells us this. It says that 25% decomposes. So the starting amount is A sub 0, whatever that is. The ending amount, if 25% decomposes, 75% is left. 75% of what? Of the starting amount. So it would be 75% of A sub 0. If we change that into a decimal, it would look like this. So we'd say the ending amount is 0.75 times the beginning amount. Same thing as saying it's 75% of what we started with, because we lose 25%. Now, I'm making a big deal of this because sometimes it tells you how much you lose, and sometimes it tells you what you're left with. Here it says you lose 25%, so you're left with 75%. Now, let's take this information and put it into an equation, put it into this formula. So 0.75 A sub 0 equals A sub 0 times 2 to the negative t over 12.4 years. Notice what's going to happen in the next step. We're going to divide both sides by that starting amount. So it turns out that we didn't need to know what the starting amount was. Now, we divided by A sub 0 or A naught, so we have to be careful we don't divide by 0, but I'm pretty sure we can assume that the beginning amount isn't 0, because if it is, why are we even talking about it? If you have 0 of something and then it's decaying, you can't. So it's safe to assume that we've got some amount of it. All right, now we have an exponential equation, and the unknown is part of the exponent. So let's change this into a logarithmic equation. So this becomes log base 2 of 0.75 equals negative t over 12.4 years. All right, but I'm trying to solve for t. So I'm going to multiply both sides by negative 12.4. Now, the 12.4s gets rid of that. The negative, well, negative t times a negative would be a positive. So now I've got t equals negative 12.4 log base 2 of 0.75. And I turned the whole thing around because I wanted t on the left. Okay. But using the change of base, this would be negative 12.5 times log of 0.75 divided by log of 2 using base 10. Again, I could have used base e instead if I wanted to. So now negative 12.4, and then the log of 0.75, close it up, divided by the log of 2, close it up. I get 5.14646. Let's see, what does it say? They rounded it to the nearest tenth. The 4 would round down, so t is about, we'll say, about 5.1 years. Okay. Any question about that? All right. Let's take a look at another example. This says carbon 14 dating. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had initially. How old is this? Or how old is it? All right, so again, we're dealing with half-life. So A equals A naught 2 to the negative T over H power. It doesn't tell us in this problem, but in the reading earlier, it tells us that the half-life of carbon-14 is 5,700 years. A bone fragment analyzed by archaeologists contains 60%. How old is it? So time is the unknown. Now, we don't know the beginning amount. The ending amount, it says it contains 60%. So the ending amount is 0.6 times the beginning amount. Now, the first problem we did, it said 25% decomposes. So we lost 25%. We still had 75%. The reason I picked this problem is because it says it contains 60%. It doesn't lose 60, it has 60%, okay? Because that's a thing that students get confused about. All right, so now 0.6 a sub 0 equals a sub 0 times 2 to the negative t over 5,700. I'm going to divide both sides by a sub 0. 0.6 equals 2 to the negative t over 5,700 power, or yeah, power. Now I'm going to change this into a logarithmic equation. Log base 2 of 0.6 equals negative t over 5,700. I'm going to multiply both sides by negative 5,700. So that'll get rid of my 5,700 and my negative. So I've got t equals negative 5,700 log base 2 of 0.6. Using the change of base formula, we'll go log of 0.6 over log of 2, and then to the calculator. So negative 5,700 log of 0.6, close it up, divided by log of 2, close it up, and I get 4,200.703887, and it says T is about 4,200 years. All righty. Any questions about that one? Okay, let's see here. This says compound interest. Hang on a second here. Yeah, let's see this one. Compound interest. If $500 is deposited in an account paying 8.5% annual interest, compounded semi-annually, how long will it take for the account to increase to, where did it go here? $800. Okay. Oh, it's compounded semi-annually. So now I'm going to use this formula. Remember, it has to be a population that's continuously growing or continuously dying to use that A equals PE to the RT power. The reason I'm hesitating is I'm looking for a particular problem. Okay, so what do we got here? If $500 is deposited in an account paying 8.5%, so P is $500 and R is 8.5%, which would be 0.085. Compounded semi-annually, so K is 2. How long will it take for the account, so the time is the unknown, to increase to $800. So the ending amount is $800. Okay. Okay. Sorry, I'm still looking for something here. I think I know why. I think it's because it was in yesterday's, and I was thinking, because I'm working on 2 different classes, I was thinking, well, I should be covering the formula. Already did yesterday. My bad. Sorry. Okay. Back to the real world. So what do we got? We've got $800 equals $500 times 1 plus R, which is 0.085 over K, which is 2, all raised to the power 2t. Okay. Now, I could take 0.085 divided by 2 and add 1 to it and get this. $800 equals $500 times 1.0425, all raised to the 2t power. Okay. So I took this divided by that plus that, and I got my 1.0425. The problem with this is that, for one, it's messy, so let's clean it up a little. I can't change this into a logarithmic equation yet. I need to get rid of the 500. Well, I could divide both sides by the $500 that is. So let's see, a couple of zeros go, 8/5, which would come out exactly to what, 1.6? If it didn't come out exactly, I'd leave it as a fraction. This is 1.0425 to the 2t power. So I had to get rid of that coefficient before I could change it around to a logarithmic equation, which is what I'm going to do now. So this is log base 1.0425 of 1.6 equals 2t. Now, to solve for t, I want to divide both sides by 2. Here's what I want to do with this, just to make it nicer to work with. Wouldn't dividing by 2 be the same thing as multiplying times a half? Is that the same? But isn't the half equal to 0.5? So what I'm going to do is I'm going to multiply both sides by 0.5. So that gives me t equals 0.5 times the log base 1.0425 of 1.6. Why did I do all that? Just to make it nicer by having that coefficient of 0.5 out in front. Now when I go in and write it using the change of base, it's just nicer to work with than if I had that whole thing divided by 2. Okay. All right. To the calculator. 0.5 log of 1.6 divided by log of 1.0425. And I get 5.646. And let's see, what are we doing here? To the nearest tenth of a year, it's about 5.6 years. Okay. What I was trying to avoid was this. Instead of having that, you'd have all of this divided by 2, which isn't so bad, but it just seems nicer to be able to put it all in like that. Okay. All right. Let's see here. How are we doing for time? We've got time for another one. So this one. In 2 years, 20% of a radioactive element decays. Find its half-life. So A equals A naught 2 to the negative T over H. Time is 2 years. We're supposed to find the half-life. Well, let's see. We've got the beginning amount and the ending amount. It says 20% of a radioactive element decays. So the beginning amount is the beginning amount. The ending amount, if 20% decays, we have 80% left, right? Okay. So that gives us 0.8 a sub 0 equals a sub 0 2 to the negative 2 over h power. Divide both sides by a sub 0, 0.8 equals 2 to the negative 2 over h power. This becomes log base 2 of 0.8 equals negative 2 over h. We're trying to solve for h, but h is in the denominator, not the numerator. So I need to get h on top. What I'm going to do is multiply both sides by h. So now I get h log base 2 of 0.8 equals negative 2. Okay. But I need h by itself. So now I'm going to divide both sides by log base 2 of 0.8. So now I've got h equals negative 2 divided by, but I'm going to use the change of base on this and write this as log 0.8 divided by log of 2. But I want to be careful because I need to quantify this whole thing as well as the little parentheses that are going to be in there. Okay, so negative 2 divided by the quantities of parentheses, log of 0.8, close up the 0.8, divided by the log of 2, close up the 2, then close up the entire thing. And I get 6.21257, etc., etc. And to the nearest tenth of a year, it's about 6.2 years. Any questions on that? Okay. I think that's all I have for you for today. So here's the deal. Tonight, you've got a few problems from 11.6, then 11.7, and the chapter review. Okay, that may seem like a ton of stuff, but 11.6, there's only just a few problems there. Shouldn't take you very long. Tomorrow, we're going to review for the chapter 11 test. That's Thursday. Friday is the chapter 11 test. Monday, during class time, we'll review any questions you want to go over there for that time to get ready for your final exam, which is this coming Tuesday. All right. So let me stop the recording.